Every number you have ever written down used a base, even though nobody told you at the time. When you write the number 407, you are using base 10, and the position of each digit tells you what it is worth. The 7 is worth 7 ones, the 0 is worth 0 tens, the 4 is worth 4 hundreds. That idea of position carrying value is the single most important thing in this whole topic. Because once you understand it for base 10, every other base works exactly the same way. The only thing that changes is how many digits you have to play with and how quickly the place values grow. So let's be precise about what a base is. A number system is defined by its base, sometimes called its radix, and the base tells you two things at once: how many different digit symbols exist and what each position is worth. Here is the rule that follows from that, and it is worth committing to memory because it catches people out constantly. For any system with base n, the digits available run from 0 up to n minus 1. Notice that the base itself is never a digit. In base 10, you have 0 through 9 arch. There is no single symbol for 10. In base 2, you have only 0 and 1, and there is no symbol for 2. This is why a number like 102 cannot possibly be binary. The digit 2 does not exist in base 2. If you see that in an exam question, you can rule it out immediately without doing any conversion at all. So we have three systems to deal with, and the key to keeping them straight is to remember that each one exists for a different reason. Denary, base 10, is the one humans use, almost certainly because we have 10 fingers. It has nothing to do with computing at all. It is simply what we are used to. Binary, base 2, is what the computer actually uses internally, and we will see in a moment that it has no choice in the matter. Hexadecimal, base 16, is the interesting one, because it is used by neither humans in daily life nor computers internally. It exists purely as a convenience for programmers sitting between the two. You will see it in memory addresses, in color codes, in web pages, and in MAC addresses on network hardware. Keep those three purposes distinct in your head because a very common exam question asks you why a particular system is used in a particular situation, and the answer always comes back to purpose. Now, why binary? Students often write that computers use binary because it is simpler or because it is faster. Neither of those is really the reason, and neither earns full marks. The actual reason is physical. A computer is built from electronic circuits, and those circuits are made of transistors that are reliably able to be in one of two states, a high voltage or a low voltage, on or off. We label those two states 1 and 0. It is not that binary was chosen as convenient, it is that two states is what the hardware can reliably distinguish. A circuit that tried to represent 10 different voltage levels would be far more vulnerable to electrical noise and would misread values constantly. So how do we read a binary number? Exactly the same way as Denary, but with powers of 2 instead of powers of 10. Look at this table carefully and notice the direction. The place values start at 2 to the power 0 on the right, which is 1, and double as you move left. 1, 2, 4, 8, 16, 32, 64, 128. That is a standard 8-bit byte. I want you to notice two things. First, the largest place value in a byte is 128, not 256. Second, if every single bit is set to 1, the total is 255, not 256. That off by 1 trips up an enormous number of candidates. The reason is that you are counting from 0, so 8 bits gives you 256 different values, and those values run from 0 to 255. Worth writing that distinction down: 256 possible values, maximum value 255. Hexadecimal is base 16, and that immediately creates a problem. Following our rule, base 16 needs 16 distinct digit symbols running from 0 to 15. But we only have 10-digit characters, 0 through 9. So for the values 10 to 15, we borrow letters. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Those letters are genuinely digits in this system, not labels. So the hexadecimal value F is not a letter in a number, it is the single digit representing 15, and it occupies one place just as any other digit would. Now here is the point that matters most in this section, and it is the one examiners most often see answered wrongly. Many students write that computers understand hexadecimal, or that computers process in hex. They do not. A computer works in binary and only in binary. Hexadecimal exists entirely for the benefit of humans, and every reason on this list is a human reason. It is easier to read. Comparing 3F against 0011111, the hex version is obviously less error-prone to read aloud or copy down. It is more compact, so it takes up less space on screen and is quicker to type. It reduces mistakes because humans miscount long strings of ones and zeros very easily. And the mapping is beautifully clean. One hexadecimal digit corresponds to exactly one nibble, which is 4 bits. That last point is why hex is used rather than, say, base 10, no? Because 16 is 2 to the power 4. The conversion between hex and binary needs no arithmetic at all. You just swap each hex digit for its 4-bit group. Finally, storage units. The syllabus is specific here and wants you to know the binary prefixes, not the metric ones. A bit is the smallest unit of data, a single one or 0. 8 bits make a byte. Then the units step up in powers of 2, not powers of 10. A kibibyte is 1024 bytes, which is 2 to the power 10. A mebibyte is 1024 kibibytes. A gigabyte is 1024 mebibytes. Note the names carefully: kibibyte, mebibyte, gigabyte, with that distinctive by in the middle. These are deliberately different from kilobyte and megabyte, which are based on powers of 10. Use the wrong family in an exam answer and you will lose the mark. So if a question mentions 1024, you are in the binary family. We will come back to file size calculations properly in section 1.3.